Hi everyone, thank you for coming to my talk on the genesis of the CPT theorem. Like Nuria mentioned, this was my master's thesis that I did at the Max-Planck, but it was a master's in physics, so it's really sort of in between the two, which I finished last March, and I wrote with Alexander Bloom, who some of you might know. So thank you to Flavio and Bernadette for inviting me to talk. What I'm going to talk about is the genesis of the CPT theorem. I'm going to talk about how the generalization of the operation of time reversal from non-relativistic quantum mechanics to relativistic quantum field theory brought about the discovery of the CPT theorem, the discovery that relativistic quantum field theories are invariant under the combined transformation of charge conjugation and space-time reflections. And in doing so, I hope to also highlight how this story is really the continuation of the story of the spin statistics theorem itself and how the two are interconnected. And I hope to also shed some light on how, despite the usually very formal character of CPT invariance proofs, a lot of the elements that go into it and that went historically into its discovery were very much physically motivated and not, well, they're still pretty formal, but with a little bit more physics and a little less math than the axiomatic quantum field theory people would present it as. So first I'll do a super short review of time reversal in quantum mechanics, and then I'll talk about the way that Pauli used space-time reflections in his derivation of the spin statistics theorem in 1940, and how that then later played into his proof in 1955 of general CPT invariance of relativistic quantum field theories. Then I'll talk about general formulations of time reversal in relativistic quantum field theory. This is all in the mid-1950s, 1940, 1950s, before the discovery of parity non-conservation in the weak interaction, before CP violation was discovered in the strong interaction. So at this moment in time, in the 50s, it was, in a sense, somewhat obscure, very few people interested in it, and then it was only afterwards that it really became very much relevant, especially in high-energy physics. So I'll be talking about different formulations of time reversal, and we'll see that there's a great deal of confusion of how one should think about time reversal, because, as we'll see, in some formulations, notably in Schwinger's, it comes together with charge conjugation. Some people would think about it as motion reversal, like a movie playing backwards. Other people, like Pauli, had a more abstract notion of reflections rather than specifically time reversal. So I'll show you how this was a gradual parsing out of what was the most interesting and maybe the most relevant symmetry of relativistic quantum field theory. And then I'll go to conclusions and open up the floor to questions. So before starting, I'd like to just give a very, very simple intuitive picture of how these symmetry transformations might be related. And this was on physicists' mind already in the 1930s and before. So if we consider a charged particle in a magnetic field, and it's going to be spinning in a particular way by the Lorentz force law, and then if we take the classical mechanics view of time reversal, where it's really like a movie playing backwards with velocity vectors reversed, then we would have the electron spinning in the opposite way under time reversal, right? So we would have a particle just like an electron, well actually in this case it would be an electron, but orbiting like a positron, right? So that would already give us some connection between T and C. And then if we look ahead to relativity theory, where we're going to say, as Pauli really stressed throughout all of this, that it doesn't make sense to think of parity on its own or time reversal on its own, but that we should really think of space-time together, then we can sort of start to intuit maybe that there's going to be some connection, something interesting to do with CPT in a relativistic quantum theory. So, world's shortest review of time reversal in quantum mechanics. If we consider the Schrödinger equation, here, equation 1, and given that this is how we describe time evolution in quantum mechanics, if we just replace t by minus t, we're going to get negative energies, like I have in equation 3. So how do we fix it? We fix it by using an anti-unitary operator. So if we look at equation 4, it's much easier to read it as an equation than the wordy thing above. But so if we evolve a time reverse state forward in time and equate that to the time reversal of the normal state evolved backwards in time. The two should be equal, that's equation 4. And that gives us this condition number 5, which is satisfied in quantum mechanics. We use complex conjugation, and this was shown by Wigner in 1932 in the case of no spin. When there's spin, you have to use a further unitary matrix. So that's all I'm going to say on quantum mechanics time reversal for now. Just keep in mind that it has to be an anti-unitary operation. And now I'll get into Pauli's spin statistics paper from the 1940s. So in 1932, van der Weyden had shown that we can compose tensors of any rank, that we can write all our field quantities in terms of spinors, in terms of irreducible representations of the Lorentz group, which I label as UJK. And so we're going to have that J plus K integer is going to correspond to boson fields and half integer to fermion fields. And if for the moment we focus just on bosons, then designating A, so J integer, K integer by U plus, and B by U minus, by Klebsch-Gordon decomposition, we're going to get a multiplication table like here in 7. So note that the U minus terms are going to change the class of the product. So U minus on U minus is going to give U plus is going to give U plus. And we have these further conditions for complex conjugation. And we have a similar multiplication table for fermions. And so if we now consider the 4 momentum, which is going to be a term of the type U minus, then we're going to get equations of motion of the form here, like I have in 8. And then you might be wondering why I'm getting into all of this. This is where PT comes in. Pauli thought, okay, non-relativistic field theory is PT invariant, so we would expect relativistic field theory, or we would want it to be also PT invariant, right? So he formulates a PT transformation that will do just that. It'll leave the equations of motion unchanged. And we have these additional plus and minus signs that are going to come into play later and going to be very important. But so here we have a PT transformation, and then Pauli says, okay, this leaves the dynamical equations invariant. Let's see what it does to observables. And so if we consider the 4 current, which is going to be 4 vector, like 4 momentum, it's going to be the U minus type. Then we're going to get terms like this one in equation 10. And under the PT substitutions that I've shown here, it's going to pick up a minus sign. So we're going to have, in the case of bosons, and here we're in a C number theory, we're not in a second quantized theory yet, we're going to get a probability current with varying sign, which really doesn't make sense. And if we do the same thing for fermions, we're going to find that the current is fine, but the energy is going to be negative. We're going to get energy with varying sign for fermions and probabilities with varying sign for bosons. So Pauli uses this to say, this doesn't make sense as a C number theory. We need to second quantize this theory. And in order to do that, we need to figure out which types of statistics the different types of fields are going to follow. But at this point, Pauli did not derive the necessity for the spin statistics theorem, so the necessity for anti-commutators for fermions and commutators for bosons, that the way that he did it was unrelated to PT symmetry. For bosons, it was related to causal commutation, so that operators with space-like distance should commute, and he found that the only way that this was satisfied was with Bose-Einstein statistics for integer spin fields. And for fermions, Marcus Fietz had previously shown that only anti-commutators will not give you negative energy. So we have, for bosons already, if you are very attentive or you know the story, already a CPT transformation, right? Because, well, this was for free fields, so the C I sort of gave away already. I told you it was a probability current, but if we consider interacting fields, if we consider a charged particle in a magnetic field, then we can interpret the 4 current that I had before with varying sign as an electromagnetic 4 current, and then the 0 component is going to be a charge, so we're going to have charge with varying sign. So this is already going to give us, in some senses, once we go to Q number theory, a CPT transformation for bosons. However, this does not get into questions of invariance or anything like that. It was really all about spin statistics in this paper. And now I'll go over time reversal in relativistic quantum field theory. So already Q number theory, starting with Schwinger's work on the theory of quantized fields 1, which has about 350 equations in 30 pages or so, where he develops an operation of time reversal that is going to require the spin statistics connection, as I'll show in a minute. So first, if we consider a reflection of time, like we did wrongly with the Schrödinger equation and got negative energy, so we just do that, then we're going to see that considering the expectation values of the form momentum and of the charge, the form momentum is going to pick up a minus sign in the spatial component, and the charge is going to pick up a minus sign. So now we have a charge with varying sign and a Q number theory, where it makes sense, it's antimatter. And we have the 3 momentum still being reversed. We still have the idea of a movie playing backwards under time reversal. If we now consider a generalized Schrödinger equation, and this is from Schwinger's paper, we're going to see that under time reflection, the differential operator, delta mu, on the left-hand side, and the 4 momentum operator on the right-hand side are going to transform differently under time reversal. The differential operator is going to pick up a minus sign on the 0 component, on the time component, and the 4 momentum, like I said earlier, is only going to pick up a minus sign in the spatial component. So we have this contradiction, and it is again because time reversal can't be a unitary operation in the quantum theory. We need it to be anti-unitary. And Schwinger is going to do that. Instead of using complex conjugation, he's going to use transposition. So we know that for Hermitian operators, transposition and complex conjugation are equivalent, like I show in equation 21. And if we consider the Heisenberg equations of motion, it's also very easy to see that complex conjugation is going to give us a minus sign with the I, and transposition is going to give us a minus sign from this identity. So far, the two are entirely equivalent. And now, if we consider the fermion rotation operator in equation 24, Schwinger is going to implement his time reflection by doing a rotation about the 0-5 plane, which is a very sort of unintuitive thing. The 0 direction is the time direction. The 5 direction is the direction of the gamma 5 matrix. So the important thing is that this allows you to rotate the time axis without changing the x, y, or z axes. And so by doing that with this operator, if we analyze a Lorentz scalar, so the basic scalar, we're going to see that under time reflection, fermions are going to pick up a minus sign. So fermions and bosons are going to transform differently under time reversal for Schwinger's formulation. And now we get back to a similar question as we had before. So how do we cancel an extra minus sign for fermions in a time reversal operation that involves transposition, that involves a reversing or a permuting of the order of operators? And that is by using the spin statistics theorem, so that when we permute fermions, they pick up a minus sign to cancel the minus sign from time reversal. And when we permute bosons, it's okay, we still get the same thing. And so in this way, Schwinger is able to get a time reversal invariant QFT, which has charge conjugation simply as a formal consequence of time reversal. And comparing the two, we see that Pauli and Schwinger really did it in opposite ways. So Pauli first said, let's formulate a space-time reflection that leaves the dynamical equations invariant, and then we see what happens to observables. Schwinger first said, let's see what happens to observables, and then formulate a time reversal invariant operation. Now, based on Schwinger's paper, which is in 1951, Lüders in 1952 had written his own paper on motion reversal, in which he noticed that there are specific instances in which the restrictions that demanding charge conjugation invariance and demanding time reversal invariance placed on certain couplings were the same. So he realized that. Schwinger also said something to the effect of sometimes you can replace T for C. And so in 1954, he wanted to investigate the generality of the equivalence between C and T. So that's what he did in his paper on the equivalence of invariance under time reversal and under particle-antiparticle conjugation for relativistic field theories. But I won't go over it because it's not especially good. It's very, very unclear. Even Pauli didn't like it at all. He described it as, he said, Lüders, who is an expert in reflections, could not really understand Schwinger's work, as his salad of unnecessary assumptions shows. So in a way, he was the one who first gave the proof of CPT invariance, but in a very convoluted way that people didn't really understand or like. And he himself was not even trying to do that. He sort of, I'm not sure that he really noticed he had done such a big thing. He really just showed that for a p-invariant theory, C and T were equivalent in his formulation. And assuming p-invariance at this point in time was fine because there had been nothing to hint that we should not do so. But so after several snarky letters from Pauli, then Pauli took it upon himself to show the world how this should be done, and really did so in a very, very nice way. In his paper for Bohr's 70th birthday, there was a compendium, and he wrote a paper for it, Exclusion Principle, Lorentz Group, and Reflections of Space-Time and Charge. So in this paper, he wanted to demonstrate the generality of the CPT theorem. He wanted to sort of outdo Schwinger, or as he called him, His Majesty Schwinger I, and show that the way he had done it was not really the most general way because he had not included parity, and presumably his formulation would not really work for all sorts of interactions. And he also wanted to put his own, I think he really saw it as his own, spin statistics theorem on firmer footing, now in the context of interacting fields. But more importantly, maybe on a more conceptual note, he was the one who really changed the question from thinking of different types of time reversal. So Lüders had written a paper on motion reversal, and then he had written a paper using time reversal of the first kind and of the second kind, and we had Schwinger using time reversal, but also having charge conjugation in there, and there were other authors with other formulations of time reversal, which were a big sort of mess. There was no clear notion of how best to think about this. And he was the one who said, okay, let's forget about all these things, let's think about general reflections. Let's think about strong reflection with an S for Schwinger, and weak reflection with a W for Wigner. I didn't make that up, that's Pauli. And charge conjugation. So let's consider these three and see what makes the most sense to think about. And so for Pauli's PT transformation in 1955, it's going to be different from his PT transformation from 1940 in the spin statistics paper. Here he's going to require that the energy be positive, and he's going to reject the idea of pseudo-vectors and pseudo-tensors. So we're going to get a forward momentum that does not change sign at all. We're no longer going to have the spatial component being reversed. The idea of a movie playing backwards is totally out the window. And he's also going to use Schwinger's inversion for the same reasons. And so this is where we can really see that if you want to have a PT transformation that it does not include charge conjugation, you can do so, but you have to take out the charge conjugation sort of by hand. You have to have a doubly anti-unitary operation. You're going to have inversion, but then you're also going to have Hermitian conjugation. And that's how he can get a PT transformation that does not include charge conjugation. And so by considering different couplings, he's able to show that requiring PT invariance imposes restrictions beyond Lorentz invariance on the Lagrangian, and that the restrictions are the same for PT and for C. So he rederives Lüders' results, but more generally. And finally, he's going to show later that for strong reflection, this is not the case. For strong reflection, transformations under the Lorentz group already uniquely determine transformations under CPT, and you're not going to need any further assumptions beyond the spin statistics theorem and Lorentz invariance to get CPT invariance. So I'll get into that proof because I'm running out of time. So we're going to go back to the 1940 way of thinking or classifying spinors, except this time the quantum number is going to be equal to 2 times the value from 1940. And so we're going to have that m plus n even is integer spin, and m plus n odd is half integer spin. And so if we consider the 2 components of a Dirac spinor, the upper and lower component, and we see that they're going to diagonalize the gamma 5 matrix with different eigenvalues, then we can generalize that transformation, which I didn't mention, but that's the transformation for the fields for CPT, which is going to reproduce everything we need it to. The gamma 5 matrix is going to act in such a way that the 4 current is also going to be reversed, and it's really going to do CPT for us. So this is going to be a generalization of that for spinors, for the irreducible representations of the Lorentz group. And so we generalize it like that, and then if we consider that the upper and lower component transform into each other, then we're going to have a transformation like here for the lower component. And if we equate the two, we find that they don't match unless m and n have the same parity. And that's going to be true for bosons. So for bosons, this already gives a CPT transformation that leaves all covariant equations covariant, and which doesn't require anything except for, so far I haven't shown you why it requires spin statistics, but it requires relativity at the very least at this point. But for fermions, that doesn't work. So the way to fix it is to include a factor of I. Then you get the right relation, and you can generalize it like this. So far, so good, but for products of 2 or more, we're going to pick up an extra minus sign for fermions. And at this point in the talk, everybody knows how we get rid of an extra minus sign for fermions in a time reversal operation that includes transposition, and that's going to be the spin statistics theorem, right? So this is how Pauli goes about the proof and shows that if one imposes spin statistics, relativity, and anti-symmetrizes all fermion products, symmetrizes all boson products, we're going to get a CPT invariant theory. And yeah, that's the proof of CPT invariance in relativistic QFT. So to conclude, I'll just give an overview of what the story is. It is that in 1940, Pauli was able to show that a C-number relativistic field theory doesn't make sense. We should really start from a Q-number theory, and he does that by using PT symmetry, and that's what he uses to motivate quantization. Then in 1951, Schwinger is able to derive directly from symmetry considerations of the spin statistics theorem, whereas Pauli had only motivated quantization with questions of symmetry, but then the actual quantization procedure had been determined through different considerations. Then in 1954, Lüders does his salad of assumptions and shows that there is a general CPT symmetry out there. And finally, in 1955, Pauli comes back and sort of gives a more pedagogical and clearer explanation of it all and shows that all you need is spin statistics and relativity to get CPT invariance. So that's my talk. Thank you very much.
Thanks. How is this related to Noether's theorem? That to every symmetry there's a conserved quantity? Because these are, I guess, discrete, not continuous.
Well, actually, Schwinger's time reflection is a continuous symmetry because it's a rotation. It's not in any way directly related to Noether's theorem. I mean, Noether's theorem is sort of everywhere in physics, but these considerations don't really play with that sort of conservation law. Yeah.
Thanks very much. That was really interesting. And I'm curious about the middle step by Schwinger.
Mm-hmm.
Can you say more about this 0-5 maneuver? Because I never heard of that before. I never noticed it. But did people at the time think this was? Did they question that? I mean, clearly he's not thinking in space-time format. He's not thinking about Kaluza-Klein. He's not thinking there's an actual, extra dimension of space. If there were, then it probably would have had the same sign reversal anyway.
Right.
So how does he describe that in the paper, and did anyone else call him on it or get confused by that?
He only puts it in a footnote. He says the Lorentz scalars are going to pick up a minus sign, like fermion scalars are going to pick up a minus sign, because we can think about it as a rotation, period. And then there's like a tiny little footnote showing basically the same thing that I did. Here, yeah. So he doesn't really go into it, and Schwinger is really on his own on this. So Pauli and Lüders were in correspondence, Pauli and Jost and other people were in correspondence, but Schwinger really was on his own. So they didn't really comment on this very much. So I'm afraid I can't give you a more insightful answer. But it is, it's sort of a weird trick to do.
It just seems very artificial.
Yeah, I think it definitely is. Yeah. But the way, so I should say that the way that he actually implements a time reversal operation is not that. The way he does it in practice when he's doing the derivation of t invariance is he just puts minus t for every t And then he also has a gamma naught matrix to act on the Dirac matrices and so on. So it's a little more complicated. I didn't go into the whole thing. He doesn't actually use that to implement the transformation. He just uses that to argue for the need for the spin statistics theorem, because he's going to say that the fermion terms are going to pick up a minus sign that the boson terms won't.
In 1957, I was a grad student, and I did it various flukes. I shared an office at MIT with Gerhardt Lüders.
Oh, well.
And Theorem also. So it was nice having such people. But there, everybody referred to CPT as Lüders' theorem.
Right.
And so the question is, what is the general consensus in terms of who is responsible for the CPT?
I think it depends where you look. Some people call it the Pauli-Schwinger theorem. Some people call it the Pauli-Schwinger-Lüders theorem. Some people, Bell did a very nice proof also in 1955 after Pauli had already given his. That's sort of more general, but also very, very elegant. So some people say that he was the first one. I think I really think that the one responsible for it is Pauli, going all the way back to the spin statistics paper, because he was really basically there in terms of the transformations he gave. He just generalized them a little bit more in 1955. But no, I don't think people call it the Pauli. Maybe we should start calling it the Pauli theorem. I would call it the Pauli theorem. But Lüders would probably disagree.
Is there any other question? No? Then we thank Andrés again.